Welcome to The Explainer. Today, we're taking a thrilling, headfirst descent into the absolute darkest, most mysterious objects in the entire universe. We're going to journey from the basic, but totally mind-bending, cosmic mechanics of how these titans operate, all the way down to the literal reality melting edges of theoretical physics. So, buckle up, because we are heading straight into the abyss. Okay, let's dive into this flight path. We'll start with the birth of a cosmic monster, scale on up from protons to ultramassive giants, and then actually fall across the event horizon. After that, we'll break the laws of physics, tackle the great information paradox, and finish off with a glimpse of deep reality. All right, Section 1, Birth of a Cosmic Monster, a Star's Collapse. You know, to really wrap our heads around a black hole, we kind of have to look at how our understanding of them evolved. Back in the 1780s, brilliant minds like Mitchell and Laplace first imagined this wild concept, an object so insanely massive that its escape velocity, the speed you'd need to break free from its gravity, would actually exceed the speed of light. Fast forward a bit to 1916, and Carl Schwarzschild uses Einstein's brand new math to prove they could theoretically exist. But get this, it wasn't until 1971 that we actually discovered the first black hole in the constellation Cygnus, and then, in 1974, Stephen Hawking completely flipped physics on its head by discovering that they actually leak radiation. We went from this quirky 18th century thought experiment to observing the most terrifying objects in the cosmos. So how exactly does one of these monsters form? Well, a massive star is basically a delicate balancing act between the crushing inward force of gravity and the outward push of nuclear fusion. But eventually, the star fuses heavier and heavier elements until it hits iron. And here's the problem. Iron fusion doesn't produce energy, it absorbs it. The balance completely breaks. In a fraction of a second, the star's core implodes at a quarter of the speed of light. If the star is massive enough, the entire core collapses into a single, infinitely dense point wrapped in what we call an event horizon. Think of this boundary like a massive cosmic waterfall. If you're swimming in a river toward a waterfall, the current slowly gets faster, right? Eventually, you cross a point where the water is simply moving faster than you could ever possibly swim. That point of no return, that's the event horizon. Gravity's pulling inward faster than the speed of light itself. Moving right along to Section 2. From protons to ultra-massive giants, the scales of black holes. Now, what's really interesting here is that once an event horizon forms, a truly mind-boggling property emerges. They have absolutely no physical size limit. None. On the tiny end, we have theoretical primordial black holes from the dawn of the universe. They might have the mass of an entire mountain, yet be no larger than a single proton. Then, we step up to stellar black holes. These are the corpses of dead stars, packing maybe 20 times the mass of our sun into a sphere just the size of a city. But then we jump to the supermassive and ultramassive monsters lurking at the center of galaxies. These aren't city-sized. These things can swallow entire solar systems whole. And that brings us to this frankly staggering number, 66 billion. That is the mass of TON 618, an ultramassive black hole measured in solar masses. It's an object so unimaginably huge that if you were to cross its event horizon, it would take a beam of light an entire week just to reach the center. I mean, let that sink in for a second. The fastest thing in the universe needs a full week just to fall to the bottom. It shines with the brightness of 100 trillion stars as its accretion disk actively devours galaxies' worth of matter. Section 3. Falling across the event horizon. The ultimate descent. So what actually happens to you if you get too close and cross that invisible threshold? Let's put you in the driver's seat and trace your descent. Step 1. As you approach the black hole, time drastically slows down. To your friends watching from a safe distance, you'd appear to just freeze, turn red, and slowly fade away. But from your perspective looking outward, the rest of the universe hits fast forward. You'd literally watch eons pass in moments. Step 2. As you cross the photon sphere, light gets trapped in orbit. It acts like a bizarre funhouse mirror. Light from behind you bends all the way around the black hole, meaning you could look straight ahead and actually see the back of your own head. Step 3. As you get deeper, the gravitational gradient becomes extreme. Gravity pulls at your feet millions of times harder than it pulls at your head. Which leads us to your options for survival. Let me just be perfectly clear here, you don't have any. Your first option is a quick death by a highly technical process scientists officially call spaghettification. That extreme gravity differential stretches your body until you are a hot stream of plasma, literally one atom wide. If that doesn't happen, theoretical physics offers a slightly different option, You die a very, very quick death. Some models suggest you'd hit a highly energetic firewall right at the event horizon and just be terminated instantly. So yeah, neither of these options is particularly great for your weekend plans. Section 4, breaking the laws of physics, inside the horizon. So the crucial point is, if you somehow miraculously survived that descent, you'd find yourself in a place where reality basically stops making sense. Inside the event horizon, space and time are so fiercely warped that every single direction you could possibly move leads only to the center. A black hole completely deletes the complexity of the universe into just 3 properties: mass, spin, and electric charge. That is it. Whether the black hole was formed from a collapsed star, a giant cloud of antimatter, or a ridiculous amount of bananas, once it crosses the threshold, the universe forgets its past identity. A black hole is fully described by just those 3 numbers. It strips all the beautiful, chaotic, complex information of reality into a terrifyingly simple format. And all of this leads to the singularity. Now, a lot of people picture the singularity as this really dense ball sitting in the exact physical center of a black hole. But because space and time literally flip roles inside the event horizon, the singularity isn't actually a physical place in space at all. It's a moment in time. It is literally the end of time. Falling toward it means falling toward your inevitable future. It's an infinitely dense point where our physics formulas just spit out infinities. It's the universe's ultimate divide by zero error, where predictability, causality, and space-time as we know it completely break down. Section 5. The Great Information Paradox. Does it disappear? All right, this is where we shift from astronomy into the absolute deepest realms of philosophy. Remember Stephen Hawking? He discovered that black holes aren't entirely black. Because of quantum fluctuations at the event horizon, they slowly leak radiation and lose energy. Over trillions upon trillions of years, they will eventually shrink and evaporate completely. But this creates the single most terrifying question in modern physics. If a black hole eventually evaporates into absolutely nothing, what happens to the information? What happens to the identity of all the things it swallowed? Here is the paradox perfectly laid out for us. On one side, we have quantum mechanics, this fundamental pillar of modern science, which states that information is indestructible. Think of it like this. If I burn a book into ash, quantum mechanics says if I perfectly collect every single carbon atom, every photon of light, and every wisp of smoke, I can theoretically rebuild that book. The information isn't gone. It's just really, really hard to read. But on the other side, we have black holes. They seem to take that book, delete all its unique properties, and then eventually evaporate into nothingness. If information is truly lost forever, then we basically have to throw out the fundamental laws of physics. And this brilliantly illustrates a mind-bending solution physicists have proposed to save our universe, the holographic principle. When information falls into a black hole, it turns out the surface area of the event horizon grows by a tiny pixel for each bit of information. The black hole is acting like the ultimate cosmic hard drive. All the 3D objects that fell in, entire libraries of cosmic information, are simply encoded and flattened onto the 2-dimensional surface of the event horizon. It's much like translating a physical 3D library into digital data on a flat 2D e-reader. The information isn't lost, it's just painted on the surface. Which brings us to our final stop. Section 6. A glimpse of deep reality. Emergent spacetime. So what does this all mean for the fundamental fabric of our entire universe? Well, if a 3-dimensional reality can be perfectly encoded on a 2-dimensional surface at the edge of a black hole, it implies something profound. Emergent spacetime. This right here is the absolute cutting edge of theoretical physics. If black holes teach us anything, it's that space and time might not be the fundamental building blocks of reality we always thought they were. Instead, they might just be illusions. Space and time might emerge from something deeper and smaller, like a web of quantum entanglement. Just like temperature is really just the emergent illusion of atoms jiggling around, the space you occupy and the time ticking on your watch right now might just be the emergent byproducts of a deeper hidden quantum code. Which brings us to Albert Einstein, who once famously said, "If you look at nature really carefully, you can catch a glimpse of something deeply hidden." Black holes were once just mathematical oddities, an accident on a chalkboard. Now they're the very keys to unlocking a quantum theory of gravity. They force us to question if the 3-dimensional world we experience every single day is actually just a holographic projection painted on the edge of reality. So the next time you look up at the night sky, ask yourself, are you looking at vast empty space? Or are you just staring at the source code of a deeply hidden universe? Thanks so much for joining me on this explainer, and I'll catch you next time.